right, guys, we're going to go on and get started with this chapter here. So, chapter 6. All right, guys, chapter 6 is the last chapter we're going to be covering this semester. So, chapter 6 is going to be the last chapter we're covering.
Sorry, I was talking about so much.
Guys, focus up here. So, the final schedule should be coming out, or they should be releasing it in like next week or next 2 weeks of when each of the finals will be taking place for each subject. They'll normally do English, math, history, science, and then electives. The day on which we're supposed to take the math tests or scheduled, we're not going to have enough time to squeeze it all in and hit that date. So it's going to be just back a day or two. Okay? It's either going to be worth 100 or 200. We'll see once we get to that point based off the homework. Yeah. The final, the test over this will be the final. Yeah, so you can still do makeup points for it. So I think there's been some chapters that are harder than this, but again, if sticking along to the homework and doing the practice problems does help. And the majority of this chapter, or this chapter is mainly going to be focused on exponential and logarithmic functions. Exponential and logarithmic functions. And what we're focused on today, guys, is exponential growth and exponential decay. Exponential growth, guys. Exponential growth and exponential decay come in the form of f of x is equal to b to the x, our function right here. F of x is equal to b to the x. And we consider a function to be exponential growth if the base, this b value, is greater than 1. If the value of b is greater than 1, it's considered to be an exponential growth function. So an example of exponential growth would be 3 to the x. And the reason we consider these exponential growth is because the amount of increase in the y values from one value of x to the next increases at a faster and faster rate. So we can plug in, figure this out, 3 to the x. And if we look at the function here, we can see it slowly increases and then shoots off. And if we look at the table, well, the values of y go from 3, 9, 27, 81, all the way up to where 10 is 59,000. So the 10th value in this function is 59,000. Well, the 12th value is 531,000, and then 13th is over 1 million. So it doesn't take long for these to get big. Yes? Okay. Yes. So that's why they consider these exponential growth, is because they're growing exponentially. So whenever we have a function in the form of b to the x, a number to the x, where the value of b is greater than 1, we consider it an exponential growth. Now we have exponential decay, which is in the same form, but the value of b is between 0 and 1. So 1/2 x would be an exponential decay. And these values are decreasing as we increase the value of x. So as we read it from left to right, it is decreasing towards 0. Now these functions here, exponential growth and exponential decay, will never equal 0 in the standard form of b to the x. Because unless we start moving the function up and down, it will never actually hit 0. There is a value, a limit, that these functions will approach. There's a horizontal asymptote. There's a line that the function will approach but never actually cross. Any questions on these here? Are you ready? The first example. All right, Trey. Yes. And why is this one decay? Because for it to be exponential decay, the value b has to be between 0 and 1. And this one is 1/2, so it's going to be decay. The first one, the value b is greater than 1, so it has to be. Mm-hmm. Yes. So if it's lower than 0, let's actually look at that function. So let's say -2 to the x. And let's look at the graph. Well, there's no graph for it. And the issue comes, and if we look at the table, because with all of these here, turn this on, we're looking at -2 to the x. And for each one of these, we're plugging in an x value. So, well, -2 to the 0 is going to be 1. That's just by definition. Anything to the 0 power except for 0 is 1. Now, for 1, so we're saying -2 to the first power is, well, -2. Now, -2 squared, -2 times -2 is, well, we're switching between negative and positive. So this is not a function. Because for a function, it needs to be 1-to-1 and a continuous graph from one to the other. And because it's doing this kind of back and forth, -2, 4, this jumping, it's not actually a function. It does not apply all the properties of a function, and that's talking about injective, bijective, and let's see here, injective, surjective, and bijective. So this kind of function doesn't actually fall into a function, so we don't look at those. But that is a good question. Because if it is negative, it's not technically a function at all. They are types of graphs, and we can work with them. They're more of a oscillation. They're kind of flipping from one to the other. Well, let's look at this one. This would be growth, because the value is greater than 1. How about this one? It is decay. Because 1/3 is between 0 and 1. So 4 to the x would be growth. And 2/3 to the x is decay. How about this one? It's growth. Because again, we just need to be paying attention to make sure, because if it's greater than 1, it's growth. If it's less than 1 but greater than 0, it is decay. Decay for 0.25. And the last one here is growth. Now we could talk about this in kind of an exponential model, so we can actually model things after it. So we can talk about exponential growth, where we have an initial amount multiplied by a percent increase or a percent decrease. So we can talk about car values as they increase over time and model that. Or we can talk about percent interest, so an amount that you gain, or O. And one of the big examples for this is compound interest. A equals P times 1 plus R over N to the NT. Talking about compound interest. But we're not going to focus too much on any of that there. And that's actually it. Now, 3 through 6, you're plugging in values. We didn't specifically say it, but it's going to give you something like 6 to the x. Find the value when x is 3 and x is -4. You're just plugging it in. I didn't think we would need to go over that, but 3 through 6 is mainly just plugging it in and getting the specific value. 9 through 18 is determining whether it's exponential growth or exponential decay. You do not have to graph it.